The lights in the northern sky are the visible record of a collision. Electrons traveling from the sun strike atoms in the upper atmosphere, and those atoms give off light. For most of human history, the cause was a mystery. For the last 120 years, it has not been. The phenomenon is called the Aurora Borealis in the northern hemisphere and the Aurora Australis in the southern. Both form in a band roughly 6 degrees wide, about 660 kilometers, 410 miles, centered on each geomagnetic pole. The auroral oval sits at around 67 degrees north, displaced from the magnetic pole by the pressure of the solar wind. The light is emitted between 70 and 300 kilometers above the ground, roughly 43 to 186 miles. Below 70 kilometers, the atmosphere is too thick. Above 150, the air is too thin to carry enough collisions. The colors come from specific atoms and ions at specific altitudes. Green, at 557.7 nanometers, is excited atomic oxygen at about 100 kilometers. Red, at 630 nanometers, is excited atomic oxygen at the top of the atmosphere. Blue and violet, near 428 nanometers, are molecular nitrogen lower down. The mechanism is now well understood. The sun emits a continuous outward flow of charged particles called the solar wind, mostly electrons and protons traveling at around 400 kilometers per second, 250 miles per second. Earth's magnetic field deflects most of this flow around the planet, forming a long, tear-shaped cavity called the magnetosphere. On the night side, far behind Earth, the field stretches out into a tail that extends several 100,000 kilometers downwind. Energy accumulates there, stored in the stretched magnetic field, and at irregular intervals it is released in a process called magnetic reconnection, the sudden rearrangement of field line topology. Accelerated electrons pour back along the field lines toward the polar atmosphere, gaining energies of a few thousand electron volts through a voltage that can rise to over 200,000 volts during intense magnetic storms. When they reach the upper air, they collide with oxygen and nitrogen atoms and lose their kinetic energy as light. The first laboratory demonstration of the mechanism was built in Oslo. The Norwegian physicist Christian Birkeland, at the turn of the 20th century, placed a small magnetized iron sphere, a Terrella, or Little Earth, inside a vacuum chamber and directed a beam of electrons at it. The electrons were guided by the sphere's magnetic field toward its poles, where they produced visible rings of light. Between 1902 and 1903, Birkeland organized the Norwegian Aurora Polaris expedition, setting up a network of observatories across the Arctic to record the auroral magnetic field. The results were published in 4 volumes between 1908 and 1913. He was nominated for the Nobel Prize 7 times and never received it. A historical anchor arrived half a century earlier. On the 1st of September, 1859, the English astronomer Richard Carrington was observing sunspots through a projected image when a brilliant white light flare appeared on the solar disk, lasting about 5 minutes. 16 hours later, Earth's magnetic field was struck by the largest geomagnetic storm in the instrumental record. Aurorae were seen as far south as Cuba, Hawaii, Colombia, and Queensland. Telegraph lines across Europe and North America sparked and failed. In one case between Boston and Portland, Maine, 2 operators disconnected their batteries and transmitted successfully for 2 hours on auroral current alone. Carrington's account appeared in monthly notices of the Royal Astronomical Society in 1860, with the now famous note that one swallow does not make a summer. A modern anchor came in 2008. NASA's THEMIS mission, 5 identical spacecraft launched on the 17th of February 2007, was designed specifically to find the trigger of auroral substorms. On the 26th of February 2008, 2 of the THEMIS probes, positioned about 1/3 of the way to the Moon, recorded a magnetic reconnection event 96 seconds before the aurora brightened overhead. The mission's principal investigator, Vasilis Angelopoulos, said afterwards that the data showed clearly. And for the first time, that magnetic reconnection is the trigger. Today, the radar arrays of the EISCAT Scientific Association, founded in December 1975 as a collaboration of 6 national research councils, with stations in Tromsø, Sodenkilde, Kiruna, and Longyearbyen on Svalbard, track the same currents continuously, measuring the ionosphere above 80 kilometers in real time. The incoherent scatter technique reads electron density, temperature, and velocity from faint radar reflections off the plasma itself. The name carries its own record. In Finnish, the aurora is revontulet, literally, fox fires. The older folk explanation was that an Arctic fox ran across the fells and its tail struck the snow, sending sparks into the sky. Sami traditions describe the lights as the torches of the dead. The phenomenon was ordinary enough to the people who lived under it to need a name, and unexplained enough to need a story. What replaced the story? A solar wind accelerated along magnetic field lines into a layer of oxygen and nitrogen 70 to 300 kilometers overhead, is the same phenomenon, more completely described. The aurora was not new in Birkeland's laboratory, and it had not changed in character since Carrington's time. What was new was the mechanism. The lights had been arriving for the whole of Earth's magnetic history, since the planet first produced a field strong enough to shape the incoming particles. The aurora is a weather pattern, not of air, of plasma. The sun is active, the magnetosphere stretches and releases, the upper atmosphere lights up where the field lines touch down. Wherever the field lines have touched down, for as long as Earth has had a field, the lights have been there to be seen.